In this video, we're going to look at the radical substitution mechanism of alkanes with halogens. Ultimately, what we're trying to do is to try and get to the ability where we can write equations for polyhalogenated products and predict possible side products. Okay, but before we can do that, we need to be able to recall and apply some terms and also know the different steps in the mechanism. Now, alkanes are very unreactive chemicals. What you'll see later on in the course is that any molecule which has a functional group presence, e.g. like an alcohol or an alkene, it's the functional group which undergoes the chemical reactions, not the alkyl chain. The reason for this is that the energy required to break the carbon-hydrogen bond or the carbon-carbon bond is too large. What we say at A level, we don't just say energy, it's the bond enthalpy, and that's the topic we will encounter later on in the course. Just think about the temperatures required for cracking, over 700 Kelvin, so that gives you an indication of just how strong these bonds are. Now, the reaction that we're studying, it's a radical substitution reaction. Now, it's a substitution reaction because an atom or a group of atoms is being replaced by another atom or group of atoms. Okay, and that's a definition that you do need to know. So pause the video and try looking at these equations, identify which atoms are being replaced by what. So what you see then is the hydrogens, or a hydrogen atom, is being replaced by a bromine in this one, and here we've got hydrogen being replaced by a chlorine. Second equation. Now, if you were to mix just an alkane and a halogen, such as bromine or chlorine, together, nothing would happen. You need to put some energy in to break one of the bonds to get the reaction started. We either need to use high temperatures, sometimes in the region of like 600 degrees Celsius, but more commonly we can use ultraviolet light. And ultraviolet light gives us just the right amount of energy to break the halogen-halogen bond. So in this case, the chlorine-chlorine bond or the bromine-bromine bond. Now, what we're going to do, we're going to look at the reaction of methane with chlorine, and we're going to look at the mechanism. The mechanism is what chemists use to try and explain where the atoms and the electrons are going throughout the chemical process. You've probably done enough chemical reactions in your lifetime to realise that just by looking at a test tube, you don't know what's going on in terms of the atoms and molecules. Okay, so what we're going to do is we're going to look at the overall equation and start to think about what's going on in terms of the electrons. So the overall equation, so these are our starting materials, what you put into your reaction, sometimes known as reactants. So we've got methane and chlorine. On the other side of our arrow, we've got chloromethane and hydrogen chloride. These are our expected products. We don't say hydrochloric acid because it's not dissolved in water. Okay. Now, the first step, why do we need the ultraviolet light to get the reaction to go? Well, it breaks the chlorine-chlorine bond because the carbon-hydrogen bond enthalpy is too high. So let's look at that. The chlorine-chlorine bond is broken by something called homolytic fission, where each atom in the bond takes one electron. So here you've got a covalent bond, which is a shared pair of electrons. The ultraviolet light breaks the bond, and each chlorine atom takes its electron that it used for to make that bond. So we say that these electrons have an unpaired electron. Any species, whether it's an atom, molecule, ion, which has an unpaired electron, is known as a radical, and that is something that you need to know. So overall, this mechanism where we're looking at where the electrons go and the atoms go, this is split into 3 different stages. Initiation, propagation, termination. Initiation has 1 step, propagation 2 steps, termination 3 steps. What I like to say is IPT, easy as 1, 2, 3. First step, initiation. So the ultraviolet light causes homolytic fission. Homolytic because upon splitting we are left with the same species, i.e. we've made 2 chlorine radicals, and that's the first step. The second stage is propagation. Now the propagation, this is where the reaction really occurs. This is where the radical that we've just formed in our initiation step reacts with one of the reactants, or the other reactants. In this case it's methane. You can see here that the chlorine radical has taken away a hydrogen and has left the carbon with 3 hydrogens and an unpaired electron. Now this makes this methyl radical. Now the methyl radical, just like a chlorine radical, is very high in energy, very reactive. And so this methyl radical, when it bumps into a chlorine molecule, will make chloromethane, which is one of our products, and it regenerates a chlorine radical. Okay, so the chlorine radical starts the reaction, and then it is regenerated at the end of the reaction. So we can say that in this reaction, the chlorine radical is acting as a catalyst. Now just let's have another look at these 2 propagation steps. So again, we've got methane reacting with the chlorine radical. Okay, so here's a displayed form of methane chlorine radical. The hydrogen is taken away. This hydrogen is taken away. It takes its electron with it to make a bond with the chlorine unpaired electron, and carbon is left with its unpaired electron here. When we write our equation, we must show that the radical, the unpaired electron, this dot is on the carbon. We can't write it after the hydrogen. And then in our second step, we've got the methyl radical reacting with a molecule of chlorine to make chloromethane, and our chlorine radical is regenerated. Okay, so if we were to combine those 2 equations, so let me just go back. So if I was to combine the 2 propagation equations, the top one here and the bottom one here, so everything that was on the left hand side we put on the left hand side here, everything on the right hand side we put on the right hand side. So then what we do is, once we've got this equation, we can start to cancel out any terms which appear on both sides of the equation. So you can see here we've got chlorine radicals on either side, so we can get rid of them. We also have methyl radicals on either side. We can get rid of them. So this leaves us with a much more simplified equation, which I'm hoping you can start to recognise is our overall equation. So in actual fact, our 2 propagation steps give us our overall equation, and maybe that's a technique you could use in an exam situation. The termination steps, there are 3 of these. Okay? The termination step is when 2 radicals combine to make a stable molecule. So you can have 2 chlorine radicals, or 2 methyl radicals, or a methyl and a chlorine radical to form their respective products. Again, just showing it using our displayed formulae. The two methyl radicals have got the unpaired electron on the carbon, and so the bond is between, the newly formed bond is between these two carbon atoms. And similarly, the carbon atom makes it, the carbon radical makes a bond with the chlorine radical here. Now, the trouble with this reaction, there are many problems with this reaction. First and foremost is that if you go to something like propane, butane, pentane, the halogenation can occur, i.e. put the position of where the chlorine or the bromine or the iodine molecule atom goes changes. So in the reaction of chlorine and propane, we get a mixture of 1-chloropropane and its positional isomer 2-chloropropane. So that's bad enough. However, even with the simple alkanes such as methane, once there's a low concentration of the starting alkane, i.e. most of that methane has been converted into chloromethane, there are still chlorine radicals left over. They are highly reactive, high energy species. They need to react, and as a consequence they will react and go through the propagation steps to form dichloromethane, trichloromethane, and even tetrachloromethane. And you see the similar problems with the with the longer chain alkanes too. Now, this is where we're trying to get to. This is our extended thinking. AQA AS level chemistry questions usually start with a halogenoalkane. So, for example, they might start with chloromethane, or dichloromethane, or even fluoromethane. And you will be expected to write perhaps initiation steps, propagation steps, and some termination steps. Remember this slide, which is this. Initiation is just the breaking of the chlorine-chlorine bond to form 2 chlorine radicals. So that's the easy step. The propagation, this is where it gets tricky. The step 1, the newly formed chlorine radical will react with the alkane or the chloroalkane or whatever it is, and it will remove a hydrogen atom, leaving an alkyl radical. So it doesn't remove the chlorine that's already in chloromethane, it just removes the hydrogen. In step 2, the alkyl radical then reacts with another chlorine molecule, Cl2, to make the dichlorinated product, or trichlorinated product, and another chlorine radical. And then finally, the termination steps are where the radicals combine to form a stable molecule. Okay? So it might be worthwhile thinking about this slide and going back and looking at the equations. So here's an example. The reaction of chloromethane with chlorine. This forms dichloromethane and hydrogen chloride. So the initiation step is the same as before. Breaking the chlorine-chlorine bond to make 2 chlorine radicals. The propagation steps are chlorine radical reacting with the chloromethane. We remove a hydrogen atom, so we're left with this alkyl or chloroalkyl radical, which then goes on in the second step to react with a molecule of chlorine to form our other product, dichloromethane, and regenerates this chlorine radical. And then your termination steps, as before, any of these radicals combining. So here we've got chlorine being formed, here we've got 1,2-dichloroethane being formed, and here we've got dichloromethane being formed. So just finally, hopefully you can after watching this video, complete all of these tasks. Thank you for watching.